Welcome to the third week of the course. This week we will again be discussing multiple regression models, but this week we will extend the concept of modeling a response variable using higher order regression. So what do we mean by that? Well, so far you have created models where the response variable was linearly related to the predictors. So recall all of the scatter plots that you have created so far have shown a linear relationship between the response variable and a predictor. And this week, there will be a slight change in that. We will consider predictors where the response variable and the predictors show a non-linear kind of a relationship. And the best way to show you what we will be working with is this participation activity 5.1.1. Let's start this and see what we get. So here you can see that we have a simple linear regression that uses a straight line relationship between a response variable y and a predictor x. So this is what you have been working with so far. Um, we have clearly worked with more than one predictor, but in all of those cases, the relationship was linear. The data kind of followed a straight line, and the correlation coefficients that you have calculated so far showed moderate to strong correlation. So now let's move on to the next slide. And here you will see that we have a relationship like that. Now, in this case, clearly this is not a linear relationship. This is a nonlinear relationship. And we can model that by adding powers of predictor variables to the regression equation. By powers, what we mean is the power that's shown here, for example. As you can see here, we have a multiple regression model where the response variable is modeled as beta 0 plus beta 1x. That's the first order term. That's what we have been working with so far. And but now we have this beta 2x squared. So what we do is we take the predictor variable and we add a squared term to it. Okay, so that is what's different this time. And the squared term allows us to model relationships that may look like this, or the data points may be sort of like a mirror image, uh, mirror image of what you see here. And we will consider that um, in some of the models that we create this week. So let's go to the last slide. Let's see what we have here. So now, as you can see, a quadratic regression model includes a quantitative predictor x and x squared. Okay, so quadratic models are those where the highest power that a predictor variable takes is 2 or squared. And quadratic models are a special case of higher order regression models. And in this case, the order of regression is squared or 2. Okay, so remember last time we did the first order regression. This time we're doing the second order regression modeling. That they are also called quadratic models. And then there will be a general case of higher order regression that we will discuss later on. So let's start the assignment prep and see what kind of model we have to create this week. So here is the assignment prep for this week. And in module 3, we will be working with second order regression model. So this assignment prep will help you prepare for the problem set this week, and we will be studying quadratic models. We're not going to go beyond the second order regression, so you can have a third order, fourth order, and nth order regression. Um, Primarily because in the real world, in most instances, first order and second order regression models are sufficient to model any response variable. And then whenever the need arises, you will notice that it's very easy to um, transfer over from the second order to the third order and then to the fourth order and so on. But in most instances, this should be sufficient. So in this problem set, step one is where you load the data set, and you will notice that this is a new data set this week. And the idea here is that we want to introduce you to new data sets so that you can appreciate how predictive modeling can be applied to so many different industries. And it's amazing that something quite simple as a regression model can be applied to a variety of problems in the world. And we're going to try to introduce you to at least 5 or 6 different data sets in this course so you can appreciate the application of regression models. But clearly, this doesn't really cover everything that is modeled using regression. Anyway, so in step one, you are given this scenario. So I highly recommend that you read this. Essentially, you are working with an economic data set now. And here are the variables and their um, and the explanation of what they are. And so it's very simple. In this assignment prep, you will use wage growth as the response variable, and you're going to use inflation, unemployment, economy, and GDP as predictors. Okay, so these are going to be your predictors, and we're going to see if we can predict wage growth based on these factors. So the first step involves reading the dataset from a CSV file called economic.csv. And um, this step is pretty much the same as the last 2 weeks. We just use read.csv method to read the data from this CSV file into an R data frame called economic. Um, and we will print the first 6 rows here. Okay, so let's print this. And you will see that this is what you will get. So here are all the variables. The nice thing here is that economy and education have uh, they have string data or text data, so they're automatically read as factor variables. So you don't really need to tell R that these are factors. Okay, so this is how the data is read, and then now let's move on to step two. So in step two, we have to do a scatter plot of wage growth and GDP growth. So as the GDP grows or the growth increases, um, there's there are more and more opportunities for the labor force or for people to find jobs. And when people find jobs, you expect that there will be fewer people who don't have jobs. And when that is the case, when you have fewer people who are unemployed, then the wages have to go up because it's harder to find people to fill new jobs or new positions. And so what happens is companies will often increase wages in an attempt to attract um, individuals who may already actually be employed. Okay, so um, so what happens is this scenario tells you that when GDP growth increases, you expect that the wage growth will increase. And so let's see if that's the case in this data set. So I'm going to print this scatter plot, and as you can see here, GDP is it's on the x-axis, wage growth is on the y-axis. That's because this is the response variable. This is your predictor. So as you can see, as GDP grows, um, wage growth increases. And one important thing to note though, is that um, it's not really a linear growth like you have been working with so far. So in the first 2 weeks, you have seen scatter plots where the increase was linear. Well, this time it's a little bit non-linear, right? There's definitely a curvature here. And this is where we can use a second order regression model, or in other words, a quadratic model to model this kind of a relationship. Okay, so that's the idea behind regression models this week. And it may be the case that you will come across, like in the real world, when if you're working in this area and you're creating predictive models, that a lot of the independent variables or predictors will have a nonlinear kind of a relationship with your response variable. So as soon as you see something like this, you should automatically think about using a quadratic model where the predictor will take a there will be a term in the model where the predictor has a power of 2. Okay, so this is step 2, very simple. And this is what you have to explain when you're doing your problem set. Make sure to be a little detailed about what you see and how it's different than the previous week. It's very important to see that difference and also appreciate the difference. Okay, so that's step 2. So let's go to step 3. In step 3, we have to create a scatter plot of wage growth and unemployment rate. So as the unemployment rate increases, we would expect that wage growth will decrease. And one of the reasons, for example, is because when unemployment rate increases, that means more of the labor force is unemployed, and that most likely means that the economy is going through some kind of a turmoil, and therefore companies are either not hiring, or if they are hiring, that they have a lot of candidates to pick from. So there's a pressure on wages to be lower. And so the wage growth will actually decrease when unemployment rate increases. So let's see if that's what we see in the scatter plot. So this step here will create the scatter plot. So let's run this. And here's the output. So as you can see, again, wage growth is on the y-axis, unemployment rate is on the x-axis. So, and as you can see, when unemployment rate increases, wage growth decreases. But notice that the decrease is not necessarily a linear decrease, right? There's a little bit of a curvature to this as well. And this again um, is an indication that maybe a second order term for unemployment rate as a predictor may be necessary in the model. So let's see if that's what we get. But clearly, again, you can see that this is another case where just by having a visual like a scatter plot can tell you so much about how you should create your model. Okay, so don't, my recommendation at least is don't just go about creating models. Study the variables a little bit as the first step. Get your visuals. See if you can get any patterns, that may tell you what kind of model to create, whether the predictor term should have a second order term or not in the model. These are very important steps because the more you study these steps, the less you'll have to do later on when you get your model. And most of the terms will end up being significant if you have created the model correctly. Otherwise, you'll just go about creating a model, and then you'll realize that, hey, some of these terms are insignificant in the model. So what's wrong? You may think, for example, in this case, the linear term, the first order term for unemployment may be insignificant in the model. And you'll ask yourself that, well, at least the intuition tells you that as unemployment rate increases, wage should decrease. So why is the data not um, significant in the model? Well, it could be the case that because you included the first order term, but you did not include the second order term that actually models this kind of relationship. Okay, so that's why the visuals are important. So this is step 3, and in the next step we will create a quadratic model. So step 4 involves a quadratic model or a second order model with one quantitative variable. Okay, so we're going to start very basic with just one predictor, and we will model the relationship for the wage growth. Now, if you recall from the first week, I briefly discussed it in my lecture, or you may have taken a course before where you studied simple linear regression for a full week. So in a simple linear regression model, you have the response variable equals beta 0 plus beta 1 x. Okay, and x is your again your predictor. Well, if you notice, this is the general form of the second order or quadratic model where you only have one predictor. Notice that this part here is exactly what a simple linear regression model is, right? This is what that is. And all you have to do is add this term here, beta 2x squared, for to make it into a quadratic model. Now, here we're considering the most basic model with just one predictor. So we can have multiple predictors, um, and just as long as they show some kind of a curvature kind of a relationship with the response variable, you can keep adding their squared terms. Okay, so you may have some, and then you can have a mixture of predictors where one predictor may have a linear relationship with the response variable, so you will not include a squared term for it, and then the other predictor may have a squared, may have a kind of like a curvature kind of a relationship um, with the response variable. So for that predictor, you can include both the first order and the second order term. Um, and that's generally true about regression modeling. That's why that visualization step is so important. Anyway, so we will start very basic. This involves one predictor, um, the first order term, and the second order term. Okay, so this is the quadratic model. So here we are modeling wage growth using GDP growth as predictor. Okay, so let's see how we're going to do this. So first of all, you'll notice that I'm using the LM function again. So the nice thing here is that you don't have to learn a new function in R to be able to create quadratic models. This, the LM function will work. And um, in this function, you will notice again we have the response variable wage growth and then the tilde sign just like before. Then we have our first predictor, that is GDP, and I'm including the first order term here. This GDP is the variable name. Um, this is the first order term that's shown here. Okay, so that's how this is again just like the last 2 weeks, nothing different so far. Well, now we're gonna add the second order term here, and for that, here's the representation. Here's how you are going to input a second order term into the model. Um, you're going to use the capital I, then parentheses, and inside the parentheses, you're going to have the predictor and then the power uh, raised to the power 2. Okay, so that what you're telling the model here is that you want the GDP as the predictor variable, but then you also want the GDP, um, a second order term for GDP um, in the model. Okay, and then this is how you are going to input this. So just be careful. Sometimes students will think that because this is x squared, so you can just take the GDP and add a term GDP times GDP. Okay, that's not how the function is sort of designed to work. This is the convention to use when you want to have a second order um, term into the model. Okay, very simple. And then the rest is the same. We're just going to take this model, assign it to this variable name here, and then we're going to use the summary um, function to get our statistics for the model. So let's run this and see what we get. So here we ran the model and um, well, the output looks just like what you've been working with in the last 2 weeks, right? You have your coefficients. The estimates are given here. Notice that you have the GDP estimate. That this is the estimate for this term, the first order term. So this is your beta 1 estimate is 1.1144, and the second order term estimate, beta 2, is given here. So um, it's very easy, right? I mean, the once you get your output, it's so simple to get your estimates for betas and then create the multiple regression model. There's nothing different beyond this step here where you had to create the second order term. Everything else is the same. Okay, so you get your estimates. Um, you you get your so here you have the individual t-tests, and you will notice that both the GDP and the first order term for GDP and the second order term for GDP both are significant. Okay, because the p-values are almost zero here. And let's look at the overall f-test here is given here. The p-value for that is also zero. So clearly that the model is significant, and you know why it's significant, because you have at least, well, in this case, both of them, but at least one of the term in the model is significant. And then you look at your t-test and you notice that both terms are significant. Um, your multiple r squared is 0.8338. Well, that's pretty good. 83% of the variation in the response variable in wage growth is explained by this model that uses GDP growth as a predictor involving two terms, a first order and second order term. So that's good. Everything else is the same, right? So again, very simple concept. Once you know that you need the second order term, this is how simple it is to create it in your model, and then the model output is the same. Okay, and now let's move on to interpretation of the beta estimates. That's always a very important step to be able to interpret what beta 1 and beta 2 means in this regression model. So once you have your estimates for the betas, you can plug them here and create your regression model equation. So this is what the model looks like. And the natural question now is, how do we interpret the beta estimates here? Okay, so remember last week the beta estimate for the first order term was that for a unit increase in the predictor variable, the response variable would increase or decrease by that beta, right? So in this case, for example, we would have said that a unit increase in the predictor, that is the GDP growth. So if the GDP growth rate increases by 1 unit or 1%, the wage growth will increase by 1.1144 percent. So that's how we would have interpreted this based on last week. But this week is different. So this is going to be a little bit different, and you have to be very careful about how you do this interpretation. Well, first of all, the simpler thing here is that this interpretation does not mean anything, okay, in a quadratic model. So here, as you can see, it says note that the estimated coefficient of term x is plus 1.1144. So in the presence of the squared term here, because we have a quadratic model, it no longer represents a slope coefficient. Okay, so this is not a slope coefficient, so you cannot uh, do the same interpretation that you've been doing in the last 2 weeks. Okay, in fact, the estimated coefficient of x, 1.1144, does not have a meaningful interpretation at all. Okay, so there's really no meaning um, in doing this kind of an interpretation when you have a quadratic model. Okay, so you just simply ignore this piece here. The second bullet, however, is about interpreting this estimate, okay, for the squared term, for the second order term. And here, the interesting thing, or the very first thing that you should look at, is do you have a negative or a positive sign for the beta, okay? So in here we have negative 0.0326, so we have a negative sign. So here the estimated coefficient of the term is minus 0.0326. Since the sign is negative, so it indicates a curve with downward concavity, okay? So let's just look at that. So if we scroll up to the scatter plot, this is the wage growth with GDP, and you can see that this relationship is not linear. So you have a curvature here, and the curvature points to a downward concavity where you could have had this going down this way. Okay, so the curve sort of increases here, but then starts a downward movement. Okay, that's why we say um, that's why we have here that it indicates a curve with downward concavity. This confirms that the relationship observed in step 2, so it confirms the relationship in step 2. That's the scatter plot that we just saw. A plus sign, so if this was plus, a positive or a plus sign for the estimate would indicate a curve relationship that has upward concavity. Okay, so there it would be going upwards, and that was the case in this case, for example. Okay, so although we did not create this, we did not include unemployment in the model, but we can clearly see that this has a curve that comes down, but then attempts to go upwards, right? And so the concavity is upward there, and for unemployment rate, if we had used that as a predictor, you would have a plus sign for the beta estimate. Okay, so that is how you interpret the beta estimate for the second order term. Okay, so what you're really doing here is you're describing the relationship that you saw in the scatter plot. But you must when you do this analysis for your problem set and in the project, please make sure to break this um, interpretation into two parts. One, indicate the sign. Start off with the sign. Is it a negative or a positive sign? And then second, talk about whether the curve has a downward or upward concavity. Okay, and this bullet here will help you do that analysis. So the next step involves the prediction, making predictions for the response variable, prediction interval, and getting a confidence interval. And the idea is this is pretty much the same as the previous week. We create our data frame of where the GDP value equals 1.7. So we want to be able to predict the wage growth when GDP is 1.7%. Okay, so we create this just like last week. There's really nothing different here. We first create our prediction interval, and then we create our confidence interval. So let's run this step. And here is, first of all, here's the prediction, 2.5136. It's going to be the same in both. And then here's the lower and the upper bound for the prediction interval, and then the lower and the upper bound for the confidence interval. This step is pretty much the same. So as you can see, all we're doing is essentially just inputting the value of GDP equals 1.7. That's the predictor. So we will plug that in here as 1.7 and here as 1.7 squared. And we get our prediction for wage growth. So the wage growth is expected to be 2.5136%. And here is the prediction interval and the confidence interval, and you know how to interpret them both. So please make sure to be detailed in your interpretation of the prediction interval and the confidence interval and what they represent and why is the prediction interval always wider than the confidence interval. So now let's work on a complete second order model that uses two predictors. So in the previous step, we just used one predictor and we created a second order model, also called a quadratic model. Now we will create a complete second order model. So what is a complete model that uses two predictors? So in this case, we have unemployment and GDP as the two predictors. And a complete second order model is one where for each predictor we have their first order terms. So like here we have x1 and x2. Those are the first order terms. We have their second order terms that are given here, x1 squared and x2 squared. And we also have the interaction between the two terms, x1 and x2. Okay, so that is what we call a complete second order model. And that's because those are all of the combinations of terms that we can come up with um, for the two predictors. And just like this, we can have a complete third order model, fourth order model, and nth model. Um, and so all of those models can be created and they would include all of the different possible combinations of variables. In this section, we will mostly be working with just the complete second order model, and you will just be introduced to the general form of the nth order model, but you will not be expected to actually do um, any models in the homework assignment for anything more than the second order model. So now that we know what a complete second order model is, I do want to emphasize one point. So suppose that x1 is has a curved relationship with the response variable, so that you want to include the first order term and its second order term. But now let's say that x2 is linearly related to the response variable, so that it makes sense to include the first order term, but it may not make sense to include the second order term. And that's totally okay. So you don't have to include the second order term for x2 if it shows a linear relationship with the response variable. In that case, it would just not be a complete second order model, but it would still be a second order model because you would have the second order term for x1. And that's okay to that's okay to go about it that way. Um, just note that again, um, regression modeling is just as much art as much as it's science. Um, you almost always have to analyze your data, visualize your data to create a model that makes sense. Okay, so in this case, for example, both unemployment and GDP have a curved relationship with the response variable, and therefore it makes sense to include their second order terms. And we are also including their interactions to see if that turns out to be significant in the model, and that's why this model is a complete second order model. Okay, so now that we know what this model is and we have the general form of the model, let's run it and see um, let's run it and see what we get. So here we have the model. Um, to code this is pretty much the same as what we have been doing so far, so that should not be any surprise to you. So let's run it and see what we get. So here's the output. So you will notice that for each term in the general um, equation of the model, you have the estimate provided here. So these are the first order terms, unemployment and GDP. Those are its estimates. We have the second order estimates given here. Okay, so this is for the unemployment squared and GDP squared. And we have the interaction term given here. Okay, and turns out that unemployment squared is significant, GDP is significant, unemployment is significant, and GDP squared is not significant, and the interaction is not significant, and that's okay. We have a multiple R squared of 0.9587, so the model is explaining almost 96% of the variation in wage growth, which is a really good result. Um, and it's also, I guess, important to note here, like when you create these models in the real world and you're working with these giant data sets with lots and lots of variables, you may find that your multiple R squared, the best that you're getting is around 30-40%. And that's actually considered pretty good in the industry, because sometimes the data is noisy, and so anything that you can extract from the data that you have, any variation that can be explained is good. Okay. So anyway, so this is the model, and we have the standard outputs given here. The interpretation of those outputs is pretty much the same as you've been doing so far. So really nothing new, except we just introduced a a complete second order model to you, and the rest is the same. So next we have the prediction interval, and the confidence interval. So now that we have two predictors, we're using two predictors here, creating the data frame of just one row, and then getting our predictions and the intervals. So let's just run this. And here's the prediction. Here are the intervals. They're just like what we have seen before. You have a lower bound and an upper bound, and then you have to do your proper interpretation of both the intervals. And again, explain why the prediction interval is wider than the confidence interval. So in step 8, we again have a complete second order model, but this time we have one quantitative predictor and one qualitative predictor. Okay, that's what's different now. Um, and here we're using unemployment as the quantitative predictor, just like before, but now we're using economy as the second predictor, but an economy is a qualitative variable. So if we scroll up, we will see that in step 1, we have, here's the economy variable. It's a factor, and you will notice that it's taking values. Either it's a recession or not a recession. Okay, so it's not numeric clearly. So how do we include that in a second order model? Well, it's very simple. We for the quantitative predictor unemployment, we include the first order term and the second order term. And for the qualitative predictor economy, we include the first order term, but it clearly doesn't make sense to include the second order term, okay? Because what would be a squared value of um, a word recession or not recession, right? That wouldn't make any sense. And it's a factor. And a factor, when R takes a predictor as a factor, it sort of creates a 0 or 1, kind of a flag variable. Okay, so 1 would perhaps be recession, and 0 would be not recession, right? And the squared of 1 is still 1, and a squared of 0 is still 0. So it doesn't really make sense to include the square term in this case. So you would only include the first order term for the qualitative predictor. Okay. You would still include the interaction term, x1 and x2, because that's legitimate. You can include that in the model. But you would also include one other term, that is the interaction between x1 squared and um, and x2. Okay, so that's what's different. Um, is what's different in this case. When you have a qualitative predictor and you're creating a complete second order model, you would be including this extra term here, and you would not be including the x2 squared term. Okay, and that's pretty much it. Once you know what model you're creating here, you have the general form of the model. You will then um, code it in R, and it's pretty much the same as before. Um, there's really not much different about this. We have the unemployment economy, the first order terms, the interaction between the two. Then we have the unemployment squared, and we have the interaction of unemployment squared and economy. So let's run this and see what we get. That's your third model for this week. And here are all our estimates and the p-values for the t-tests. Clearly, the overall f-test is significant, so you would go back and look at which terms here are significant. Please make sure when you explain this in your problem assignment that you clearly lay out what the null hypothesis and the alternative hypothesis is for the overall test, for the overall f-test, as well as the individual t-test. It's very important to clearly specify what the hypothesis test is testing. Okay, and then here are all your statistics that you can use to explain the utility of the model, how good of a model you have. Okay, and then the next step is again prediction interval and the confidence interval. And this time we're using the unemployment as a quantitative predictor and economy as a qualitative predictor. So we're creating this one row, and then doing our predictions. So let's see what we get here. So here is our prediction of the wage growth of 2.74%. And here is the lower and the upper bound of the prediction interval and the confidence interval. And so those are the three models that we will consider this week. The homework assignment also includes similar models that you have to create. Clearly, you're going to be given different predictors, but the idea will be the same. So I hope you were able to follow this lecture, and make sure to read the textbook as well. It has really good examples that will solidify your understanding of second order models, quadratic models that use one predictors and more than one predictors. And we will continue regression next week into more sophisticated models. And then the last few weeks are really exciting because they involve some machine learning models.